This is the first part of the replacement lecture for the Anzac Day lecture on Tuesday, and it's about hypothesis testing errors. So the point about hypothesis tests, or statistics in general, is, or statistical inference in general, is that we're trying to draw inferences about the underlying population based on a sample which is much, much smaller than the population. So we don't have all of the possible information about population, and so the conclusions that we come to when doing statistical inference are not always going to be correct. And the point of studying statistical inference in some detail is to try to understand what errors could be made and what factors influence the probabilities of making those kinds of errors, and ultimately, hopefully, trying to control and even perhaps minimise the possibilities of making these kinds of errors. So there's a lot that can be said about this, and we won't get too far into the messy details, but this lecture will just give you an introduction to how we think about these things in statistics. Right, so the setting is this. We're going to continue talking about testing a hypothesis about a mean, a population mean mu. Now all the concepts, we will talk about more hypothesis tests, different kinds of hypothesis tests very soon in QM1. And the concepts that we're going to bring in today about these errors will apply to those tests as well. But for the time being, it's sufficient to introduce the ideas just to talk about testing a mean, as we have been doing. So we have a null hypothesis that the population mean mu is equal to some given number, m, we will know. And I'll specifically talk in this lecture about an alternative hypothesis which is two-tailed, so that mu is not equal to m. But again, if we talk about this one, then all the concepts and ideas carry over immediately to these kinds of one-tail alternatives as well. I mean, in a sense, doing the two-tail case is the most general one here, because we need to look at kind of both sides of the null hypothesis. All right, so what we do is we formulate these hypotheses. So we've got some particular value in mind of interest for the population mean, and then we gather some data and do some statistics and then make a decision. And the language here is important, so let's just dwell on that for a minute. The decision that we make is expressed in these terms. We decide, after doing the statistics, we get our mean and our t-statistic and calculate a p-value or a critical value, and decide either to reject the null hypothesis or to not reject the null hypothesis. Okay, those are the two conclusions that we might come to after a hypothesis test. Okay, so using those words is important. One thing that we shouldn't do is say that we accept any hypothesis as being correct. So in particular, if we don't reject the null hypothesis, it's not good practice, it's not good wording to say, well, therefore we accept that the null hypothesis is true. Okay, because just because we do not reject a null hypothesis does not mean we have enough evidence to conclude that it must be true. We'll talk more about that as we go over the next lecture or two, and you'll see why that must be the case, that we can't be accepting that null hypotheses are true. All right, what we want to talk about here, though, is are the possible outcomes that we could arrive at through this hypothesis testing procedure, and how they relate to what's going on in the population, kind of the true state of nature, if you like. So here's a little table which captures the possible outcomes, the possibilities. So the decision that we're making on the basis of the hypothesis test is going to be either do not reject the null hypothesis, or we do reject the null hypothesis. So ultimately, after we do our statistics, we're going to come down on one side of this or the other, okay, on the basis of the statistics. Now, in the population, there is some true value for mu that in general we don't know, obviously. That's why we're testing a hypothesis about it, because we don't know it. But in the population, this value for mu has a true value, and that true value is either equal to m or not equal to m. Now, we don't know which is which. But if it's the case that the true value for the population mean is equal to m, and we do not reject the null hypothesis, then we've made a correct decision. Okay, so the true value for m is the one. The true value for mu is the one that we've specified, and we're not rejecting the null hypothesis that it takes that value. That's a correct decision. That's good, right? Similarly, if in the population the true value for mu is not equal to m, take some other value besides the one we specify, and then we do our hypothesis test and we reject the null, then that's also a correct decision. So rejecting the null that mu is equal to m when the truth is that mu is not equal to m, that's a correct decision. So hopefully our statistics will, as often as possible, land us in one of these two corners of this table, where we're making correct decisions on the basis of our statistics about what's going on in the population. Now, of course, statistics are not perfect in a sample, and so we can make errors. And this is an error we've already spoken about in the previous lecture, which is the error that occurs when mu really is equal to m. So the null hypothesis here is true. Okay? But we do our statistics and we decide to reject the null hypothesis. So that would be an error. That's the wrong decision. And we also have kind of the flip side of that, of this error here. We haven't spoken about this one yet, but we will today in this lecture. If the true value for mu is not equal to m, but we do not reject the null hypothesis, okay, then that's also an error. Okay, because if mu is not equal to m, then the null hypothesis is false. And if we do not reject that null hypothesis, then we've made the wrong decision. Okay, so these two errors here are the ones that we want to focus on here and to understand what influences the probabilities of these two errors occurring. Now, we saw in the last lecture that there's a particular name given to this error here. That's called a type 1 error, when we reject the null hypothesis, when the null hypothesis is actually true. And we saw how that related to the significance level of the test. And I'm going to remind you about that in a minute, and we'll go through that and illustrate that again. That's a very important idea, and it's worth refreshing. So if you're going to be doing these kinds of hypothesis tests, then it's important to know what this significance level, what this 5% thing is really measuring. So that's worth dwelling on. Now, as you can probably guess, this error down here, where we do not reject the null, when the null is actually false, well, that's a type 2 error. Okay, so, and again, we haven't met that one yet, but we'll talk about that one in the second part of this lecture. Alright, so that characterises the full set of possible decisions that could be made and how they relate to the actual values, the actual value that mu might take in the population. Now this can help, I think, is to relate this to a situation which is completely outside of statistics pretty much, which is this looks a lot like what goes on when there's a trial in court for a criminal. The logic is very much the same, and sometimes it can just help to keep things clear in your head if you imagine the kind of analogy with a criminal trial. At the very least, you can imagine those that you've seen in movies and TV, given that you probably haven't seen many statistical hypothesis tests on TV shows, but probably you have seen quite a few criminal trials. Now, in a criminal trial, the null hypothesis is that the alleged criminal is not guilty. So this is kind of the presumption of innocence, if you like, where we start off from the starting position that the criminal is assumed to be not guilty. And then the process of the trial is that evidence is presented, and on the basis of that evidence, the verdict is then either to say that the criminal is guilty, so that this null hypothesis of innocence is rejected in favour of the alternative hypothesis that the criminal is in fact guilty, or alternatively the defendant is declared to be not guilty, in which case we do not reject the null hypothesis. And in these kind of legal matters, these use of words are also kind of important, that the criminal is declared to be not guilty. They're not actually declared to be innocent. It's just that there's not sufficient evidence to decide that they are guilty. Okay, so it's not necessarily finding that they're definitely innocent. It's just that there's not enough evidence to say that they're guilty. And that relates to this point here as well, that we don't accept a hypothesis. Okay? So just because we do not reject a null hypothesis, we don't accept that it's definitely true either. Just that there's not enough evidence to reject it. Okay? So we'll come back to that point in the next lecture. It's an important one to remember. If you look at the possible outcomes for a criminal trial, they all match up, right? So there is a truth out there about what this criminal did. Let's assume it's clear cut that either the criminal or the alleged criminal, if you like, was innocent, or that they committed the crime. Now, in the court, no one knows for certain, but they're trying to make a decision on the basis of the evidence that's being presented. And on the basis of that evidence, the verdict might be not guilty, and if the person actually did not commit the crime, then that's the correct decision. But if the verdict is not guilty when the person did commit the crime, then that's an error. Now, I've just put in the statistical terminology here. This is not legal terminology. You won't hear about court cases ending in type 2 errors, but the idea is exactly the same. Okay, so if the verdict is not guilty, or when the person did commit the crime, then that's an error, clearly, and that corresponds to a type 2 error. Similarly, if the verdict is guilty when the person did commit the crime, that's a correct decision, but if the person is guilty when they were in fact, or the verdict is guilty when in fact the individual was innocent, then that's an error, and statistically we call that a type 1 error. So kind of what we're doing in a hypothesis test is we're setting out this null hypothesis about a value for the in this case the mean in the population, the mean mu, and we're putting that on trial. Okay, so this is what's going on trial, is that the mu is equal to this specified value, and we're gathering some evidence in the form of statistics, and the trial is the hypothesis testing process of doing the test statistic and the critical value or p-value. And this is the verdict. This decision to reject or to not reject the null is the verdict of the trial of this null hypothesis right here. Okay. So what we're going to talk about is, are these errors. And first of all, to return to this type 1 error, which we did talk about in the previous lecture, and we'll recap it now in the particular context of a two-sided hypothesis test now. So for a two-tailed test, the null hypothesis, or the hypotheses are like this, just as we've seen, m is a given number. The way that we tested this hypothesis was first of all to specify and calculate a t-statistic, which is the sample mean x bar minus the hypothesized value, so that's a number, m in here, and then the s divided by square root of n on the bottom line. Okay, so that's something we calculate. And if the null hypothesis is true, then this t-statistic is at least approximately t-distributed. And this t-distribution is what we use to calculate either p-values or critical values in order to come to a decision about whether this t-statistic is far enough into the tails of the distribution to decide whether or not to reject the null hypothesis. So the decision rule for a two-sided or two-tailed test like this is we will reject the null hypothesis if the t-statistic is either far enough into the upper tail of the t-distribution, so this is kind of suggesting that the x bar is so far above m that we should say that the null hypothesis does not hold, or alternatively if the t-statistic we calculate is smaller than the negative critical values, that's in the lower tail of the t-distribution. And if that's the case, we also reject the null, because then it looks like the x bar is far enough below m that it doesn't support that as being a reasonable value. Alright, so this distribution here, this approximate t-distribution, suggests that, and it holds if the null hypothesis is true. This is important. Okay, so if the null hypothesis is true, in other words, if mu is equal to m, then this t-statistic is the same as x bar minus mu, and the central limit theorem is working here, and when we divide by S, we get the t-distribution. So that's from a couple of lectures ago. Okay? So if the null hypothesis is true, then the probability that the t-statistic falls into either tail of the t-distribution defined in this way is equal to alpha. This is our significance level. Okay, so we choose this significance level, usually 5%, but sometimes other numbers. And that is corresponding exactly to the probability of rejecting the null. Okay, so this is our decision rule. We will reject the null if either t is above the critical value or t is below the critical value. So what we're saying here is if the null hypothesis is true, then the probability of rejecting the null is equal to alpha. So this alpha is being defined by the very construction of our decision rule here in such a way as the probability of making a type 1 error is equal to alpha. This is a type 1 error. If we reject the null hypothesis when the null hypothesis is true, that's a type 1 error, and the probability of that is alpha. Okay, so we've seen this. This is the same definition we've seen before. There's nothing new about that one. And then the significance level is the probability of making a type 1 error. So the way that we set up these hypothesis testing procedures is that we directly set this probability of making a type 1 error. Okay, so we know what that is. Usually 0.05, 5%. But if you want to be more careful, right, if you want to have less probability of making a type 1 error, then you can choose a different significance level. You can choose a significance level of 1% if you like. And then you'll be less likely, obviously, to make a type 1 error, rejecting the null hypothesis when it's true. Okay, so as the statistician, this is something that you get to choose. Well, I guess as a student it will more often be simply given to you, but ultimately this is something that we get to choose in statistical practice, the value of this alpha. This is not a new picture. We've seen this. This is just a kind of the diagrammatic representation of this decision rule that we've just been talking about here. So this is the two-tailed test decision rule. So this is the t-distribution here. This is being plotted, I think it was with 90 degrees of freedom. So that the exact details of that don't matter so much. What's important here is that we take this t-distribution, notice it's centered at 0, and kind of on either side of 0, here are the critical values. These red dots are these critical values that are being spoken about here and here. Okay, so this critical value here would be the t alpha on 2, and in this case the alpha is being set to 5%, so alpha, or 0.05. So here's alpha on 2 is 0.025. So this critical value is t 0.025, and then the degrees of freedom. And any value of the t-statistic above there, above that critical value, would lead to a decision to reject the null hypothesis. And similarly down here, the negative of that critical value, any value of the t-statistic down here would also lead to a decision to reject the null hypothesis. So this is the two-tailed nature of this testing problem. So either large values in this tail of the distribution or small values down in this tail of the distribution will lead us to reject the null hypothesis. And when the null hypothesis is true, there is a probability of 0.025, okay, 2.5% of ending up here, and a probability of 0.025 of ending up here. And when you add those together, it's telling us that overall there is a probability of 0.05 of rejecting the null, which leaves the rest in here. So there's a probability of 0.95 of not rejecting the null hypothesis when the null hypothesis is true. Okay, this is the t-distribution. This is the distribution that applies when the null hypothesis is true. And that's why these probabilities here are representing this significance level. Okay, the probability of rejecting the null when the null is true. It's kind of an important proviso to this. You've always got to be careful with these calculations, whether you're doing the calculation as if the null hypothesis is true, or as if it is not. So for the time being, while we're talking about a type 1 error, we are talking about when the null hypothesis is true. Okay, so let's now illustrate this numerically. So here is a spreadsheet of the class test marks that we've seen before to illustrate things in previous lectures. So what we've got here are these marks, and there's a total of 1368 of those marks. Okay, and what we're going to do is try to illustrate the type 1 error and significance level using this as our population. Okay, so ordinarily, so in this case we're saying we have access to the full population, which is nice for illustrative teaching purposes, but of course in practice this is not something that we would have available to us. So first of all, let's just calculate mu, which is the population mean. So I'm just going to call that mu there, and that will be the average of all of those marks from there down to there. Okay? So that looks like that. I'll bold that. And that's might justify it. Looks nice that way. Okay. So mu in this case is equal to 15.92032. Alright, so that's the population mean. Now we're going to be interested in testing the null hypothesis that mu is equal to m for some value. So let's put into this cell a value for m. Now what I want to do in this case is to illustrate the idea of a type 1 error, which means I want to illustrate the idea of what's the probability of rejecting the null hypothesis when the null hypothesis is true. So the value of m specifies the null hypothesis. Okay, so I'll just mention here h0 is that mu is equal to n. Okay, so m in this case, let's make that equal to the null value. Okay, so I've just hit equals and then selected that. So that means that I'm setting the value of m in such a way that now I know that the null hypothesis is true. I'm in this special situation of being able to observe the population mean. All right. So those two are now the same numbers, obviously. All right. Now what we want to illustrate here is what happens when we test that using a sample. So we've done this kind of stuff before, right? So we're going to select here a random sample. Let's make it of 20 individuals. So a fairly small sample actually, but it'll do for our purposes. So we'll go equals rand between, and we have 1368 in total. So these are our randomly selected students. Okay, so this is row number 117, and let's copy that down to there. That would be 20, wouldn't it? So if we copy that down to there, we've then got our randomly selected students, right? Or the rows, okay, out of there. All right, so let's now translate those into some marks corresponding to each of those. Now notice as we do stuff, we've seen this in all of these kinds of situations, when we're drawing these, taking these, this is a simple random sample from this population, and each time I do something it'll update the sample. So I'll just let it do that rather than locking it in place, because once everything here is set up, then I do want to take repeated samples. So let's just ignore the fact that these numbers change for the time being. Alright, let's grab the marks. So equals index. I'd encourage you to be doing this, by the way, as you go. So pause the video if you need to and try and keep up and be replicating this as I'm doing it. This spreadsheet's on the LMS. Now you won't necessarily get the exact same numbers because you will get different random samples. Okay, so don't worry about that. Just worry about getting the structure of this spreadsheet to match what I'm doing here. So I'll have the index, and I've defined an array called population, which is In fact, all of those marks, we saw this in a previous video as well, and you can see it's kind of highlighted over there. And this is corresponding to that number. So it's picking out row 88 and grabbing the mark for row 88, which has obviously now been updated. And we'll copy that down to that range as well. Whoops, paste. There we go. So now we've got ourselves a sample of 20 marks. So it's a simple random sample drawn from this population over here. Alright, now what I want to do with this simple random sample is to replicate a hypothesis test. So the hypothesis that we're testing is the null that the mu is equal to m, where m is given by this number. So from here on, we're proceeding as if all that we have observed is the sample. Okay, over here, we did observe the population, but let's come over here and forget that we observed the population and simply calculate the hypothesis test that we would get on the basis of this sample of 20 that we've drawn here. So to do that, first of all, we're going to need obviously the sample mean. So let's have a cell for x bar, which is going to be the average, let's spell average, of this range of marks. There we go. Okay, so we've got an average there of, in this case, 16.65. That'll change in there, of course. Now, what else? We're going to do a t-test, right? So think about what is included in the t-statistic. We have x bar in the top line minus m, so we've got that stuff. And then on the bottom line of the t-statistic, we have s, which is the standard deviation, and we have n, which is the sample size. Alright, so let's go for S here, the standard deviation, so equals stdev s of this data. Those 20 observations, that. Okay, so that's S, we want n, which is the sample size, which is 20 in this case. And that's all that we need in order to calculate the t-statistic, right? So the t-statistic is equal to the x bar minus the m, which is that one, okay, that's the top line, divided by the standard deviation, which is that one, and that standard deviation is itself divided by the square root of n, which is that one. So you can kind of see that formula there. If we finish up the brackets, that formula there replicates exactly the form of the t-statistic. Okay, x bar minus mu divided by s divided by square root of n. Okay, that's our t-statistic right there. In this case, 0.138. Okay. Now we need to make a decision, right? We've calculated the t-statistic, and then we need to use that t-statistic to make a decision about whether to reject the null hypothesis or not. So we could look up a critical value, or we could use a p-value. The p-value is kind of convenient, so here we go. Here's the p-value. Now this is a two-tailed test, so we're going to replicate what we did in the previous lecture and use the t-distribution in its two-tailed form. And we're going to put in here the absolute value. So this two-tailed t-distribution command requires the t-statistic to be positive, so just to have its magnitude included. So the absolute value is being applied to the t-statistic there. Okay, so this is something you need to do when you're doing a two-tailed p-value calculation, is to take the absolute value of that t-statistic. Okay, if you're doing a one-tailed calculation, you don't need, in fact you shouldn't take the absolute value like this. This is something we only do in the two-tailed case when using this .2t command. Okay, so that's the absolute value of the t-statistic, and then we better have some degrees of freedom. The degrees of freedom are n minus 1, so we'll select n there and put in the minus 1, and that's it. That should calculate the p-value for us, and there is the p-value. Alright, with the p-value it's then simple enough to make our final decision about the hypothesis, whether to reject or not. So that will be, first of all, we need obviously a significance level, which I'll call alpha, and that can be 0.05. And just to make things really clear, we can have a decision And the decision rule is we are going to reject the null hypothesis if the p is less than 0.05 and do not reject if the p is greater than 0.05. So obviously you can see with that number there, the p-value is greater than 0.05, so we would not reject the null hypothesis. It'd be nice to have some words in here. So here's what you could do. You could say this cell is equal to if the p-value, if the p-value is less than the alpha, okay, comma, then we're just going to print here reject h naught. How about that? Okay, so if that condition is true, if p is less than alpha, then this cell will contain reject h naught. And if it's not true, and so notice there it's helping us out here. So the logical test, if j2 is less than k2, so if p is less than alpha, then say reject h naught. And then if it's false, so if this condition is false, then we will print out do not reject h naught, like that. And that will hopefully do. There we go. So in this case, the p is now 0.96, which is bigger than alpha, and so the decision is do not reject the null hypothesis. All right. So what we've got in this sequence of cells here is kind of spelt out in quite a bit of detail what you do to set up a t-test for a mean equal to a specified value, and to calculate the p-value, and then to make a decision in the two-tailed case. Now in this case, because we have access to these population values, then we know that the hypothesis that we're testing is in fact true in this case, because we calculated the sample mean and then chose to test the null hypothesis being a value that's equal to that sample mean. So every time that we draw a sample of size 20 and calculate this sample mean, we know that this sample mean is trying to estimate this population mean. It's an unbiased estimator of this population mean. And the correct decision over here for this hypothesis test is do not reject the null hypothesis, because here the null hypothesis is true. Alright, so in this particular set of numbers, for this random sample that was drawn when we finished clicking last, we have come up with a conclusion of do not reject the null hypothesis. So that's correct, okay? This random sample of size 20 has led us to a correct decision in this case. Now what I want to show you is what happens when we repeatedly draw random samples. And this is the idea of trying to get, at least intuitively, a picture of what the probability of making a type 1 error is. So in this setup, if we drew a different random sample from this population and ended up with a decision to reject the null hypothesis here, then that would be a type 1 error. And what's interesting to see here is if we start now repeatedly drawing random samples, how often we see a rejection of the null hypothesis coming up here. Now all the theory that we've done would suggest that we should have a probability of rejecting the null of 5%, okay, or 1 time in 20 roughly. So what we'll do is I'm just going to start recalculating this spreadsheet, so just kind of hitting the command equals, and each time I do that it will draw a new sample of individuals and a new sample of marks and recalculate the x bar and the s and the t statistic and the p and come up with a new decision. And let's do that, say, 20 times. I don't know how this is going to work out because it's random, right? But what we would expect is that, roughly speaking, we will get 1 rejection in the next 20 times that we draw a sample and carry out the hypothesis test. So let's see what happens. Oh, okay, so there we go. The very first time I've pressed Control equals. So the second sample that we've drawn, we have a rejection of the null hypothesis. So in this case, the sample has drawn an x bar, has got an x bar of 17, which is far enough above the population mean of 15.9 to give us a p-value of 0.03, which is less than 0.05, and we've rejected the null. Okay, so out of two samples that we've looked at, the first one did not reject, which was correct, and oops, this one did reject, and that's an error, a type 1 error. Okay, so we have one type 1 error so far. Let's see how we go. I'm now going to draw another sample, and this time we do not reject. Okay, p-value 0.4 is above the 0.05. Okay, so that's 3 samples now. And our fourth sample, again, we do not reject. So you can see the sample being redrawn, the marks being redrawn, and then the rest of these statistics being recalculated. Okay, so 5 do not reject, 6 do not reject, 7, oh, we got another one, we do reject, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, oh, another one, 20. So, in this case, we ended up getting 3 type 1 errors out of the 20 samples that we drew. Okay, so the theory would suggest that we got 1. So we got two more than what the theory would suggest. If we kept on going, and I'm not going to make you suffer through sitting here me going control equals lots and lots of times, but if we did that lots and lots of times, then what we would see is that the percentage or the proportion of times that we got a rejection would get closer and closer to 0.05. This is the relative frequency kind of concept of probability that we're dealing with here. So we're repeatedly drawing random samples. We know that the probability in any one of those of rejecting the null is 5%. And we're getting, well, we only took 20 replications and we got 3. So it's not very many, right? In 17 of those 20 we made the right decision. And in 3 of those we made type 1 errors. Okay, so that's kind of that's the concept of, so the type 1 error is making the wrong decision, okay, rejecting the null when we shouldn't. And then the significance level, this 0.05, is the probability of the type 1 error. So we're controlling the probability of a type 1 error by specifying this number here. Okay, and if we change that number, we will be changing the probability of rejecting the null incorrectly. Okay, so we'll stop there, and then in the second part of this lecture, take a look at the type 2 errors.